The next algorithm in swarm intelligence is ant colony optimization, or ACO. This video will describe this algorithm, so let's start. Ant colony optimization is inspired from how ants forage or search for food. Individual ants, when they are walking, they will lay a pheromone trails, and when they are traveling from the nest to the nest or possibly in both directions. So for example, if this is the nest of the ant and this is the source of food, so when the ant is moving to the source of food, it will lay down a pheromone trails, and when the ant finds the food and brings back the food to the nest, this pheromone trail will be reinforced. Pheromone trail will evaporate gradually over time. However, the trail strength will accumulate when multiple ants are using the same path. Ants lay down pheromone trails when it is moving. An isolated ant moves at random, but when it finds a pheromone trail, the ant will have a high probability of following the trail. As ant forage for food, it will deposit pheromones over its root. So you can see there is a pheromone trail over here. And when it finds a food source, it will return to the nest, thereby reinforcing its trail. And if you can see that this pheromone trail is now reinforced. So going back to this particular point. So if you have a pheromone trail over here, and there is a random ant moving randomly, and then this ant discover this pheromone trail, it will then follow along the trail. So when it found this food source, the ant will carry the food and follows the pheromone trail, go back to its nest, and it will use the trail over again, which means this trail will now get reinforced, making it a higher probability of other ants to follow the trail from the nest to the food source and from the food source to the nest. And this is how ants communicate with each other, through the pheromones laid down on its trail. Going back to the previous example, when other ants from the same nest discover this trail, it follows the path that has been laid down, therefore laying more pheromones on it. This process works as a positive feedback loop, and the higher the pheromone intensity of the trail, higher chance other ants start to travel on it. Let's look at how pheromone trails work. There are two sources of nest in this path. So we have nest at location A, nest A, and we have nest at location E, nest E. In the middle of the nest A into nest E, there is an obstacle. The paths are divided into two. The first path is BH path with a distance of 1. And the second path is the BC path with a distance of 0.5, half the distance of path BH. Meanwhile, at D, the path is also divided into two. Path DH has the distance of 1.0, and path DC has the distance of 0.5, which is half of DH. At timestamp t equals to 0, 30 ants move from nest E and 30 ants move from nest A. So when they reach B, half of the ants will follow the BH trail because currently there is still no pheromone trail. Therefore, the probability is 50-50, and another 15 ants will go through the BC trail. Same goes at location D. The 30 ants that comes from nest E just now will be divided equally at this path. 15 will go through the DH trail and another 15 will go through the DC trail. At the next timestamp, the 15 ants that go through this path just now would have arrived at B, because remember, the distance of DC and BC are half of DH and BH. Therefore, this trail would have a larger amount of pheromone trails or larger intensity of pheromone trails as compared to this trail. And at timestamp 1, when another group of 30 ants comes from nest A, they would have a greater probability of following this path because the pheromone at this path is stronger rather than this path. This is how a shorter path is always chosen by a group of ants through the reinforcement of pheromone trails. This is another visualization of the same situation we discussed in the previous slide. So if you have a group of ants moving from the nest to the food, and suddenly an obstacle appears in the middle of the path. When they first started moving, it is the group of ants will be divided 50-50. Half would go through this path, another half would go at this path. However, since this path is shorter, it means a larger amount of ants would arrive faster here. Therefore, this path is reinforced more. The pheromone here is reinforced more as compared to this path. That's why at the end, the group of ants would have a larger probability of following this path as compared to the longer path. The indirect communication via interaction with environment is named as stigmergy. And this highly sophisticated way ants collectively perform complex tasks is due to stigmergy. They communicate using pheromones and they leave trails of pheromones that can be followed by other ants. Okay, now let's discuss how exactly the concept of stigmergy and ant colony is used in AI. So the basic idea of this algorithm are ants are agents and they move along between nodes in a graph. These agents will choose where to go based on the pheromone strength and perhaps some other factors. An ant's path, once it finished circulating, represent a specific candidate solution. And when an ant has finished a solution, pheromone will be belatedly, meaning after the tour is completed, according to the quality of solution. So if the tour cost is less, the amount of pheromone that is laid would be stronger. However, if the tour distance is huge, pheromone will still be laid, but in a lesser amount as compared to the other solution. Of course, these are all very problem specific, and the famous example that is used to demonstrate the capability of ant colony optimization is the famous example of the traveling salesman problem. Pheromones on edge's path also decrease by certain percentage for every cycle. This is evaporation property, and it is also observed in nature because in nature, pheromones will decay. This procedure will then be applied repeatedly until a termination criterion is satisfied. Let's look at this traveling salesman problem with 4 cities example, or TSP4. From each city, it is possible to travel to all other cities with varying distances. The purpose or the ultimate mission is to find the shortest path that a particular agent can use, in which it will go through all the cities and go back to the starting cities, and we are finding the shortest path. Initially, random levels of pheromones are scattered on the edges. So if you look here, so we have these pheromones laid down at the edges of the path, and these are all randomly assigned. The strength of these pheromones are randomly assigned. And then we have this path, and all this path has several distances. During initialization, an ant will also be placed at a random node. So let's say this is our ant, and his name is Anthony. Here he is located at city B. From city B, Anthony will now decide which city to go next. His choice will be based on factors such as pheromone strength, next hop distances, and other factors. So let's say he decides to go to city C next. Once Anthony arrives at city C, he has the memory of having been to B and C, so he will not visit these two cities again. Anthony will now decide to go to the two remaining cities, city A and city D. Suppose he chooses to visit city D. Our Ant-Man is now at city D, and the tour memory now includes city B, C, and D, which means there is only one more city that Anthony can go, and that is city A. He now has to return back to the original city he was first placed on. By going back to city B, Anthony has finished his tour. He went through the links of BC, CD, DA, and AB. While we were looking at the journey of Anthony, at the same time, other ants were also doing their tour. They started with different cities and they may have followed different paths. Let's say we have 3 ants doing the experiment. Ant 1 is Anthony, and the path he took was BCDAB, and the tour course or the distance is 100. Ant 2 is Anjali. The path that Anjali took is ACBDA, and the tour distance is 95. And Ant 3 is Annie. So Annie took the CDABC path, and the distance or the tour course is 110. In this cycle, Anjali has the best solution because the distance or the tour cost is 95 compared to the distance of Anthony and Annie. Therefore, the path that Anjali took, which is ACBDA, would have its pheromones increase the most. The path that Anthony and Annie took will also have their pheromones increase, but not as high as Anjali's path. The pheromones are updated based on the quality of the solution. The pheromones, meanwhile, will also be decreased everywhere, and this is done to model decay that also happens in nature. The path he didn't take was AC and BD. Therefore, while the link or the path he took, the pheromone will be increased, AC and BD will remain the same. Notice that all the path that Anthony took, the pheromones have been increased, while the path that he didn't take, the pheromones stay the same. Next, pheromones everywhere will decrease a little, and this is to model decay of trail strength. You will see that all pheromones, including at the path that Anthony took, their strengths have been decreased. But since they have been reinforced just now, we still see a significant remained of pheromones. However, the path that Anthony didn't took, the pheromones, it seems they are almost disappearing. As long as we have not met the stopping criteria, the whole process will start again with the updated pheromones. Anthony will now be placed in a random city position. Suppose he is now placed at city D. Where will he go? Again, the choice will be influenced by factors such as pheromone strength, distance, and others. This is the ACO algorithm for traveling salesman problem, and this is summarizing what we have discussed with the example of Anthony, Anjali, and Annie. So we have a TSP with N cities, and we place some N's at each city. Each N will then do this. When all N's have completed their tours, global pheromone updating occurs. So this is where the current pheromone levels on all links are reduced, while pheromone are lain belatedly on all links of the tour, and the strength of pheromones is depending on how good the tour was, how good the solution was. Then we go back to 1 and repeat the whole process many times until we reach the termination criterion. This is the algorithm in the form of flowchart. So we initialize, we place N randomly in chosen city, and for each N, it will choose the next city for each N. And if you have more cities to visit, the process will be repeated. However, if you have finished visiting all the cities, return to the initial cities, update the pheromone level based on the tour cost, and if you have reached the stopping criteria, you can stop and print the best tour. And finally, this is the algorithm in the form of pseudocode. It is always a good idea to understand and memorize the flow of this pseudocode. So in a loop, randomly position m number of n's on n number of cities, and for city 1 to n and for n 1 to m, each n will build a solution by adding one city after the other or visiting one city after the other. The probability of the next city to be selected is based on the exploration and exploitation mechanism. The factors would include pheromone strength, the next distance, or other factors. And then apply the local trail updating rule. And then N for all N's and N for all cities, and apply the global trail updating rule using the best N. And you end when the termination criterion or termination condition has been met.